Suppose we have a rectangular loop of conducting wire that's sliding along on a frictionless surface or drifting through space or something, and it goes from a region where there is no magnetic field into a region where there is a uniform magnetic field. So, what happens as our wire loop begins to enter that region? We have reason to believe that something will happen because as it enters the region, the magnetic flux through the loop will be changing, and we know from Faraday's law that that will induce a current in the loop. So we're going to look at three different parts of the story. First, where the loop begins entering the region, then later when the loop is entirely within the region, and then lastly when the loop is leaving the region as it continues to move to the right. Okay, so entering the B field region, our steps for applying Faraday's law start with computing the magnetic flux through our Amperian loop here, a loop that lies right on top of our rectangular wire loop. I've already picked a direction dA outwards to be parallel to our B field outwards, and so then our dS's go counterclockwise by right-hand rule. So B dot dA, the flux is zero in this half of, or this portion of our area here. There's no B field over here. Our B field only begins right here. So only this area has B field passing through it. The area of that area is the length L times this distance here, x. I'm calling that x, which will be a function of time. As the wire loop drifts inward, x increases. More and more of the loop is inside the region. So specifically, x is the distance from the edge of the B field region to the right edge of our wire loop. That's increasing with time. So our flux is the B field strength times this area here, that length times x of t, that changing area. So here we're going to get a changing magnetic flux, not because the B field is changing, it isn't, and not because the size of the loop is changing, it isn't, but because the loop is moving through a non-uniform B field, from a region where B is zero to a region where it is not zero. That's why we've got a changing area, this changing area, where the B field is actually penetrating through our loop. Okay, so next step, we need the time derivative of that magnetic flux. ddt of this, B and L are constants, so we have dx dt. And the rate of change of x right here is exactly equal to the x component of the velocity of the wire loop. So dx dt becomes vx here, so the rate of change of flux through the loop depends on the speed at which the loop is moving to the right. So there we go, we've got a changing flux. Next, apply Faraday's law. We will have an induced EMF and an induced current in our loop equal to the opposite of the rate of change of that flux, so minus BL times the velocity of the loop. Since the velocity is a function of time, the current and EMF will be functions of time as well. Let's think about Lenz's law and this sign and the direction of our current. Let's see here. Since we've got flux coming out of the page, and as the loop moves into the region, there's more and more outward flux, so the system will respond by trying to reduce that outward flux. So we're going to get a clockwise current clockwise induced current during this time, so that clockwise current can add magnetic flux into the loop to oppose the increasing flux out of the loop. So clockwise would be opposite the direction of our DS's, so this clockwise current will be a negative current, hence the negative sign right here. Since V is positive, I, our current, will be negative, and the EMF would also be considered negative as well, driving that negative current. Negative meaning here clockwise, opposite the direction of ds. Now that we've got current running through our loop as the loop begins to enter this region, some parts of our loop are going to be feeling magnetic forces, field type forces, electromagnetic forces. So IL cross B forces. In particular, this segment here on the right with a current coming downward will feel a force IL crossed with B, thumb pointing to the left. There will be a leftward force on this segment right here, given in with a size given by this expression. This is our ILB. So our induced current times the length L times the B field strength along that wire. Let's see, I here is negative, indicating that that force is in the negative x direction. Or explicitly subbing this in for I, we get this expression, and we see that our force is pointing in the opposite direction of our velocity. It is indeed a drag force, and it is a linear function of the velocity. It depends on not v squared, but just v right here. So there's our linear drag force. We know that'll lead to an exponential decay in the velocity as the loop begins to enter. So the loop is going to slow down, its velocity decreasing exponentially as it enters this region. Our magnetic drag force has the effect of trying to resist the entry of the loop into the region. It's trying to keep the loop out. Once again, serving the purposes of Lenz's law, serving the purposes of that electromagnetic inertia. The magnetic force shows up to try and prevent the loop from entering a region, because entering the region is changing the flux through the loop. Our force is opposing that changing flux through the loop, trying to keep the loop out of the region. Note also that part of the top wire and part of the bottom wire are also in the magnetic field region. And so there's a current running this way through the top wire and that way through the bottom wire. So those parts of the top and bottom wire that are in the region, they are going to feel filled type electromagnetic forces as well. So looking at the top section, we'll have IL cross B. So IL crossed with B points down. Bottom section, IL crossed with B points up. So there'll be electromagnetic forces like this and that on those two segments, acting just on this part of the wire that's in the B field and that part of the wire that's in the B field. We see they're opposite in direction, so they'll cancel each other out. There'll be no net force in that direction, but overall, these three forces will have the effect of trying to compress or contract the loop and push the loop out of our B field region. The size of those two forces, we should note, the size of those two field forces there upon entering the B field region will depend on IL cross B, but the L here would just be the length of wire that's actually in the magnetic field region. So that would be this distance we've been calling X right here. So as the loop enters that region, these two forces here on top and bottom will depend on the current, and also, which is a function of time, and also depend on X, which is a function of time, and then B right there. So this is not big L here, this is not this L, and it's also not this total distance here, it's just the distance, just the length of wire that's actually in the B field. Okay, well, that opposing force is going to be slowing down our loop, but we know we're going to get an exponential decay in the velocity, so the velocity will not go to zero, not until time approaches infinity. So our loop is guaranteed to eventually make it all the way into the region. And look at what happens when our loop is in that region. Once inside, we can apply this whole set of reasoning again. We can find the magnetic flux through the loop. So here the loop is inside. It's still got some velocity to the right. This will be a lower speed than here because we know it's slowed down as it was entering, but it's still moving to the right. And our flux here, we've got a uniform magnetic field throughout this whole area. So if our loop has dimensions L and W, W there for that distance, then BLW is our constant with respect to time magnetic flux through that loop. So there is a flux through the loop while it's inside, but that flux is not changing. Its time derivative is zero. L and W are not changing. B is not changing. So the loop is moving. It's moving through a magnetic field, but through a uniform magnetic field. So no change to the flux, therefore no induced currents, no induced EMF. So our current stops running during this time, no current at all, which means no electromagnetic forces on our wire loop. So its acceleration will be zero, therefore its velocity will be constant. Apparently, once the loop fully enters the region, Once the left-hand segment here makes it inside, then no more changing flux. That loop will continue to drift at a constant velocity all the way through to the other edge of that region. Just in case it was unclear, I noted that our loop here has some resistance that I've just denoted by this little resistor over here, representing the total resistance of our loop, which appears here. That R is the total resistance of our loop in Faraday's law. Okay, lastly, let's look at leaving the region over here. We're going to go through those steps once again. Note this time that the length of segment that's still inside the B field region would be this length W minus this length X. Now we're going to call X the distance from the edge of the region to the right edge of the wire loop. So this X will be increasing with time as the right edge of the loop moves further and further out of the region. So this distance here is then W minus X. This distance here is still big L. Leaving that B field region, we're going to find the flux through that loop, B dot dA. So it'll be B times the area that is still inside the region. That is big L times W minus X. This area here, just this area is still inside the region, so that's what determines the magnetic flux. And this area is getting smaller with time as the loop drifts to the right. So there's our flux as a function of time. Let's find its time derivative. So B and L are constant. We need d dt of W minus X of t. W is a constant. That's just the fixed width of our loop. So then minus dx dt, or BL times minus Vx. This flux is now decreasing in contrast to the flux when the loop was entering the region. In that case, the flux was increasing. Now it's decreasing, as indicated by this minus sign right here. So for a positive V, our rate of change of flux is negative. Flux is decreasing. Apply Faraday's law, and our EMF equals IR equals minus d phi dt. So that minus sign and that minus sign cancel to get plus BL Vx. We get a positive EMF and a positive current instead, suggesting that this current is going to be running counterclockwise. Counterclockwise is the direction that goes with our DS's, so that's our positive direction here. Let's make sure that makes sense from a Lenz's law point of view. We've got outward flux, and as the loop is leaving, that outward flux is going to be decreasing. Less and less of the loop is in the B field region. So we've got an outward flux that's decreasing. We're losing outward flux. So the system will respond through its electromagnetic inertia, trying to maintain that outward flux. So a counterclockwise induced current in the direction of the DS's, that will be adding B field outwards, trying to replenish the B field that we're losing out of the page, replenish the flux that we're losing out of the page as the loop leaves this region. Okay, there's our counterclockwise current in the same direction as the DS's, which is, by our conventions here, a positive current. So there we have it. Now look at our drag forces we're going to get this time. Once again, it'll be the primary drag force will be that on this time the left-hand segment here. So let's do IL cross B, IL cross with B, pointing to the left. So our electromagnetic force, our Philb type force on that wire, is pointing to the left, as it was when the loop was entering the region. There was a drag force trying to prevent, at this time, the loop from entering the region. Now it's a drag force trying to prevent the loop from leaving the region. So based on our formula here, IL cross B, there's a negative sign right there, since this I was positive and this L was this way. So L cross B points in the negative X direction. Hence that negative sign right there. This I is positive. Subbing in this expression for the I, we get the minus comes over, and once again we have a linear drag force. There's the drag part, there's the linear part, and we know that that's going to lead to an exponential decay in the speed. Looking at the other two segments here that could feel forces, that little segment right there and that segment right there, they'll feel forces. Let's look at the top segment, IL cross B. IL cross with B points up. Bottom segment, that force will point down. So we'll have these two forces as well, equal and opposite. So they will be canceling each other out, but are having the net effect of like stretching the loop out, trying to make the loop bigger, trying to maintain the outward flux in the loop. Just as this drag force is trying to prevent the loop from leaving the region, trying to maintain the flux at what it was. And so overall, look at sort of how our electromagnetic forces are behaving here. At first, it's like, don't come in, don't come in, don't come in. It's trying to push it out, don't come in. Once you're inside, okay, you're good. You're fully in now. You can stay here. So it just drifts along with that flux. And then once it's trying to leave, like, wait, don't leave, don't leave, don't leave. Come back, come back, come back, come back. And it's pulling it backwards, trying to prevent the flux from changing here by trying to keep it out, trying to prevent the flux from changing here by trying to keep it in. So we'll be slowing down while entering, slowing down while leaving. And if we made a graph of the velocity versus time for our loop, here's our loop drifting at some initial constant velocity before it enters the region. When the front edge enters, then we have that changing flux and an exponential decay. Once the back edge enters and our loop is fully inside, we drift at a constant velocity across. Then as the front edge begins to leave, we get an exponential decay once again from our changing flux. This should take longer than before, perhaps since we're going slower here, although you could consider the details of these relative time durations yourself. Then once the back edge of that loop leaves the region fully, then the loop is fully outside the region, no more changing flux, and should continue on at a constant velocity thereafter.